On September 19, 1957, executives and scientists of the National Reactor Testing Station in Idaho assembled in a control room to witness the birth of a powerful new nuclear test reactor, the largest known facility of its type. Its name, the Engineering Test Reactor, or ETR. It is a major development in the United States Atomic Energy Commission's program to advance construction of economic nuclear reactors for civilian and industrial use, and to convert aircraft and ships to nuclear propulsion. The reactor is being used principally to determine the effects of intense neutron and gamma ray bombardment in large-scale testing of fuel elements and reactor components under conditions to be met in nuclear power plants of the future. Two outstanding features of the ETR design are bottom positioning of the control rods, leaving the top of the reactor free for experimental access, and providing large experimental spaces within the heart of the core. The ETR is water-cooled and moderated with U-235 enriched fuel, both beryllium and aluminum as reflectors, and has a power rating of 175 megawatts. It will produce heat fluxes ranging from 440,000 BTU per hour per square foot to a maximum of 1,150,000 BTU. It will provide an average thermal flux of 4 times 10 to the 14th power and an average fast neutron flux of 1.5 times 10 to the 15th. These conditions will be equal to, or in many cases exceed, those likely to be found in any reactor for which components are to be tested. The test reactor idea is not new. The Engineering Test Reactor was pioneered by the Materials Testing Reactor located right next door at the National Reactor Testing Station in the state of Idaho. The Materials Testing Reactor, known as MTR, has been in operation since 1952. The MTR was the first high-flux test reactor built in the United States. It is a thermal or slow neutron reactor with U-235 enriched fuel, water as both coolant and moderator, and beryllium as the reflector. Its basic purpose is to provide data on materials' performance and characteristics within an environment of intense nuclear radiation. The experimental facilities consist of spaces within the beryllium reflector and several beam hole penetrations in the shielding and tank extending right up to the core. The Materials Testing Reactor has over 100 experimental positions, but was not designed for in-core testing, nor for irradiating large samples, such as full-size prototype fuel elements intended for power and propulsion reactors. Rapid advances in reactor technology dictated the need for testing on an engineering scale. While the MTR will still continue with work on smaller materials samples and experiments of a research nature, the ETR, just a few yards to the south, is the next step forward in the crucial testing program. The design of the Engineering Test Reactor was derived in part from a conceptual design study prepared by Phillips Petroleum Company, operators of both the MTR and the ETR. Construction was begun late in 1955. Design and construction had to be accomplished almost simultaneously. The work was done for the Atomic Energy Commission by a single architect-engineer-constructor, Kaiser Engineers. They, in turn, assigned the nuclear design project to the General Electric Company. Construction proceeded on schedule, even through sub-zero winter temperatures. Kaiser Engineers used their nationwide system of offices to expedite the manufacture of components at the various subcontractors' locations. Vigorous liaison between the Atomic Energy Commission, the many contractors, and the Phillips Petroleum Company dovetailed all facets of the big project. And late in December of 1956, the reactor building was ready to receive the huge reactor pressure vessel. The 150,000-pound pressure vessel was fabricated in Boston, Massachusetts, some 3,000 miles from Idaho, and was delivered on special railroad equipment. Shipping difficulties made it necessary to remove some of the exterior equipment, such as nozzles and flanges, which were replaced upon arrival. The vessel is made of carbon steel with interior cladding of stainless steel. It is about 35 feet long and 12 feet in diameter at the top, with a lower section diameter of 8 feet. The pressure vessel is supported on a bed plate at the transition level, from the larger to the smaller diameter. This support method provides for thermal expansion of the vessel diametrically without excessive stress or movement. The pressure vessel is designed for 250 psig at 200 degrees Fahrenheit and will operate at 185 psig. All design criteria were established with similar safety factors included. The point of highest pressure will occur on the bottom head of the vessel due to the weight of the water column. It has a cluster of perforations to accommodate the control rod drives and experimental loops. The bottom head will be subject to periodic loads as high as 20,900 psi under full scram conditions. This assumes an optimum combined weight of more than 180 tons for the grid plate, internal thermal shields, water, core components, experimental facilities, and control rod shock load. In its final position, the vessel protrudes a few feet above the top floor level of the reactor building and extends downward 3 stories to the sub-pile room. Particular pains had to be taken in the fabrication of the grid plate. Since this is the positioning device for the core components, extremely high tolerances were imperative through every phase of manufacture and machining. Before the basic forging was complete, 2 blanks had to be rejected. The grid plate is 9.5 inches thick and 62.5 inches in diameter. The various perforations will guide the control rods, position the fuel elements, and accommodate the experimental facilities. The close tolerances exercised in the machining of the grid plate provide precise control over the positioning of the core components, plus such structural support that an upper grid plate will not be required. In operation, there will be a combined thermal and mechanical load on the plate of 16,300 psi. The grid plate is positioned at the bottom of the inner reactor tank, midway in the narrow section of the pressure vessel, and is supported by stainless steel I-beams 8 feet long. Directly below the grid plate, positioning pads prevent excessive lateral motion. Through the supports, the grid plate load is transmitted to the bottom head of the pressure vessel. The core structure is built upon the grid plate in the following arrangement. There are 49 fuel elements, surrounded by a beryllium reflector 4.5 inches thick, an outer reflector of aluminum sections, plus a permanent aluminum blanket. There are 16 control rods within the fuel section, and 2 regulating rods located in the beryllium reflector. The neutron source is also located in the beryllium reflector. Finally, there are 17 openings in the core and reflector for experimental facilities. The control rods for the Engineering Test Reactor are unique, not only in positioning, but also in design. 4 of the 16 control rods are called black poison rods, the poison section consisting of boron-enriched Type 304 stainless steel. The 12 remaining rods are called gray poison rods, the poison being Type A nickel, low in cobalt content. Each rod consists of a poison section at the top, a fuel section in the middle, and a shock section at the bottom, assembled end to end. This assembly is latched to a drive mechanism which moves the fuel and poison sections in and out of the reactor core through a guide tube. The shock section does not enter the core. In operation, the black poison rods are used in startup and shutdown, while the gray rods are used for operational control. In low position, the gray rods will overcome 12% excess reactivity. In shutdown, the black rods will handle 14.4% excess. The 2 regulating rods in the reflector are of the black poison type, each capable of overcoming 0.5% excess, and are used as the reactor fine control. The fuel elements for the ETR are flat plate-type aluminum boron uranium assemblies. Each element contains 19 fuel plates, 37 inches long, positioned in the side plates so that there is a coolant passage between the plates. The incorporation of a burnable poison, boron, in the fuel element extends the useful life of the fuel and provides more uniform flux distribution in the core. Since performance characteristics of the core depend largely upon the contents of the experimental spaces, a low-power mock-up of the ETR core was set up in an adjacent building. We're concerned here only with nuclear parameters, so this low-power core assembly provides us with valuable data which are applied in setting up an experiment in the ETR. Thus, prior to any proposed test, proper core loading, control, and behavior are determined here, saving much actual reactor operating time. Since the control rod drives are located at the bottom of the reactor, all of the space at the top level is free for experimental facilities. In addition, access to the core is simplified. The penetrations of the active part of the core range from 9 by 9 inches to 3 by 3 inches and extend for the length of the core, or 36 inches. Facility tubes may be inserted in the spaces, providing for external control of experiments during operations. In a typical experiment, for example, of the single-pass air loop type, the test material will be placed in a facility tube, which also permits circulation of air. Radial penetrations of the shielding and vessel could accommodate several such experiments. Instrument leads will be attached, and in some cases, mechanical linkages for specimen manipulation can be provided. The tube leaves the reactor through the bottom head, where a 90-degree turn leads it through a port into the basement, where it is routed to the stacked discharge system. Other experimental loops utilize access sleeves within the outer shielding. These are high-pressure, closed, recirculating water loops. The lines run from bottom floor cubicles through the reactor shield to the sub-pile room, then to the reactor top via access sleeves in the concrete biological shield. The lines enter the reactor vessel through the access nozzles, pass down through the core, and out through access holes in the reactor bottom plug into the sub-pile room. The lines leave the sub-pile room and re-enter the cubicle through the access sleeves in the sub-pile room wall. All of the experimental services, such as fluid circulation and heat exchange, power supply, and instrumentation, are connected externally and don't interfere with reactor operation. Still another category is the package loop, in which the circulating pumps and heat exchanger are integral parts of the loop entirely contained within the reactor tank. Access to the loop is through a nozzle in the upper part of the reactor vessel. The reactor also can accommodate a large number of capsule-type experiments. In operation, the top of the reactor is shielded by removable concrete sections, assembled in an igloo-like arrangement, completely closing off the top of the reactor. Early in construction, prior to the arrival of the reactor vessel, an external thermal shield was installed. It is made of lead, 3.5 inches thick, in which stainless tubing is embedded. Primary system water is circulated through these tubes for cooling. In addition, an internal thermal shield is placed around the core between the inner reactor tank and the pressure vessel walls. The inner shield consists of 4 concentric steel cylinders, each 57 inches high, separated to allow the flow of water. This design feature was dictated by the 175 megawatt power output of the core. The combined stress on the inner shield is 2,200 psi, which is less than 10% of its yield strength. The external and internal thermal shielding surrounds the core area in general and will serve to limit the temperature at the inner face of the concrete biological shield to 120 degrees Fahrenheit. The reactor is cooled by demineralized water flowing at about 44,000 gallons per minute or at 35 feet per second through the core area. It enters the reactor through a 36-inch pipe in the upper vessel. The water is then deflected upward by a flow distributor. The distributor, by changing flow direction, minimizes turbulence and hydraulic loads on internal installations and acts to dissipate input vortices and vibrations from the pumps. The water reverses and flows down through the core and back up along the internal thermal shield to a 36-inch discharge pipe. These pipes are located in a shielded tunnel that leads to a separate heat exchanger building, where the reactor fission heat is transferred to a secondary cooling system, both systems being separate loops. From the secondary loop, the reactor heat is dissipated through conventional cooling towers. The Engineering Test Reactor operates on a 20-day cycle. In that period, average fuel burnup will be 33%. The absence of top controls greatly simplifies the change-out procedure. Long grapples are used with special grasping hooks to engage the fuel element handle. Once the fuel element is engaged by the grapple, it is passed through a nozzle in the reactor tank and deposited in a transfer chute. This opening is closed during reactor operation. The transfer chute at the reactor end of the canal is hydraulically operated, tilting away from the reactor vessel at an angle that permits easy removal of the spent element. It is grappled from the chute and placed in one of the storage racks in the canal. During startup operations, a high water level in the canal was not necessary. In normal operations, the canal is filled for maximum shielding, since the activity rate of each element exceeds 1 million Roentgens per hour. In the working area of the canal, there is a remote-operated saw, which allows the operator to cut irradiated material into convenient lengths for storage or handling. The canal is a T-shape with a 60-foot storage canal and a 35-foot working area in the stem of the T. The canal is a uniform 20 feet in depth, except for this well, directly under the transfer chute. The junction of the two canals may be sealed with a removable bulkhead, permitting separate drainage of each section. The storage section is 60 feet long and 12 feet wide, allowing ample room for manipulation of equipment. The compressor building adjoins the reactor building and houses air compressors and heaters for experimental facilities. 30 pounds of air per second at 320 psig pressure is supplied from here. Also, 24 pounds of this air can be heated and manifolded into a single header for experimenters' use. The ETR-MTR electrical facilities for general power and experimental power have been greatly expanded. The power requirements for the ETR area alone consist of a connected load of 17,800 kilovolt amperes, of which 8,000 kVA is of test facilities. Formal ceremonies late in 1957 officially dedicated the Engineering Test Reactor to private industry and the vital research necessary to the rapid development of economical and plentiful nuclear energy. The full design core loading was reached September 26th, 1 week after criticality had been achieved, and the post-neutron test continued for many weeks, during which the reactor's operational behavior was observed at increasing power. Certain difficulties related to the mechanical stability of the first batch of fuel elements became evident during pre-neutron testing. It was found also that the fuel had a higher than design content of the poison boron because of metallurgical and analytical uncertainties, with resultant lower than design excess reactivity. However, solutions to these problems were found, and by early 1958, the reactor was running at approximately 90 megawatts, the full power required for the first major experiment. With this first experiment completed, other experimental loops were installed, and the power was increased as needed up to the design value. This, in essence, is the Engineering Test Reactor, its design, purpose, and scope. The Engineering Test Reactor marks a distinct advance in test reactor capabilities. This film on the design and construction of the ETR was prepared by the United States Atomic Energy Commission to promote understanding of our activities in the development of such facilities and their relation to the nuclear power program.